So in the previous video, I defined the basic structure of probability and emphasized the the importance of sample size, repetitions, right? You have to repeat the experiment many times to have a accurate probability, okay? And based on that idea, we are going to define two important terms in statistics which is not well known, right? So most of you have not heard about these yet. One is population and the other is the sample. So think about this in the coin toss example. We already know the answer. 50%. The answer, the probability of heads is 50%. But also you know that even I try 1,000 times, I repeat 1,000 times, the probability is not exactly the truth. So what you can see here is the true probability is different from the probability you calculate. We have to distinguish them, right? So, and in the end, in the statistical inference, what you want is, what you're going to do is like this. There is a true probability. True probability is here, like 50%, but actually I don't know. I don't know the true probability, or I'd like to check if the true probability is actually 50%. And to do that, to estimate the true probability, you calculate the probability from your data, from your observed results, right? And you are going to estimate the unknown true probability using the calculated probability. So that's what we are going to do in the end. And to as a foundation for that, we will think about the population. First, sample is simple. This is the observed results, observed outcomes. But before defining the sample, we are going to define population, which is the limit, right? So if the sample size, if the number of repetitions approaches to the infinity in the limit, you are going to get the true probability, right? It's pretty simple mathematical definition. The limit of the calculated probability is the true probability. So we are going to then define the limit as the population. It's the collection of all possible things. Collection of like infinite repetitions, all items, right? So sample is like the population means all items. In this case, item is like, say, when you toss a coin, so you will, like, there is a physical trajectory of the coin until it goes up and down. So physically, if you can describe all those movements of the coin, that's a population. When you throw a coin, the coin will follow one of the trajectory. But actually, when you throw 1,000 times, you are going to observe only 1,000 trajectory out of the population. There can be infinite possible movements, but you only observe 1,000 of them. That's a subset of the population. So this is the mathematical definition of data, right? So data is just a part of what is over there. Over there, beyond the data, actually there are infinite number of things, but we cannot observe all of them because they are infinity. So we are going to take some part of them, subset of them, that is our observations. That's our data, that's the sample. So as opposing terms, like we call them the population and the sample, okay? So simply speaking, you can think about this. You can think like this. The population is the observations, the data when you repeat the experiment for an infinite number of times, right? Of course, it is not possible. It is not possible, but mathematically, we can think about the limit. That is the limit, and that is the true probability. So truth is when you have infinite observations. Of course, because we don't know this, because we cannot do infinite times, So we need statistical inference. That is our story in the future in chapter 8, 9, 10. So, okay, right? So, and yeah, we cannot approach to the population, so we have a sample as a part of the population, and we study the relationship between them. That's inference. Let me talk about more concrete example. Survey data. So survey data is a type of data we often use. Survey is very common, especially in social science. You ask different people. So then let's think about how these data are generated. We will think about the underlying structure for a survey. Basically, the experiment is randomly choosing a person, right? So, say household survey means you are randomly choosing a household, random household, or like business survey is to randomly choose a business, right? So like that, survey data, the randomness in survey data, randomness is coming from randomly choosing a subject, right? And then from there you get outcome. Once you choose a subject, you ask a lot of questions like, right, what is your income, what is your revenue, and what's your age, what is your demographics, like things like that, and record their data. You observe their answers as data, right? So that's how survey data is generated and how we understand survey data as within our framework, unified framework. So you can think about experiment and how the randomness is generated. Okay, and there are many commonly used survey data. I list these names in case if you'd like to do some kind of research for like in other courses or for your independent research, maybe these are good starting points, right? Panel study of income dynamics, like like observes income over time, income dynamics, and current population survey. CPS data is really popular. It's a huge sample size about basic demographics, socioeconomic variables. National longitudinal survey of youth. This is a very interesting data. This is about youth, which means you can study like the results of like the impact of education, the youth and their parents, what happened in their teenagers, right? And health and retirement study. This is about aging people, health and their retirement decisions, pension, things like that. Consumer expenditure survey is about consuming behavior, consumption behaviors, and like the recessions, booms, economic trends. And survey of consumer finances, like it's about savings, things like that. So depending on your interest, one of these may attract you. Then I recommend to use them like for your research if you're interested. Another common type of data is time series. So this is more tricky, like especially if we follow the frequentist approach. The definition we learned, in the definition, I said we have to repeat experiments. But sometimes we cannot repeat an experiment. Oh, that's the problem. Like for example, think about this. I would like to study the probability of rain on Labor Day. Suppose that I say it's 30%. So we need to think about this probability. We have to calculate that probability for forecasting. Someone has to forecast that. So probability itself is not hard to understand, but the problem is it does not fit well to our framework. Our structure does not allow repetition of Labor Day, right? So we imagine a very weird experiment. Purely imaginary, hypothetical experiment is like this. Say, suppose that there are a lot of possible weather scenarios, right? Think about, so in weather forecast, you see like map with like clouds, wind, and rains, like humidity, temperatures, like pressures. There are like a lot of measures over like areas around here in this region, and the Mother Nature chooses one scenario based on that, right? So, and I assume that every year Labor Day is actually the same, right? So, this year's every Labor Day is similar to the same repetition of previous Labor Days, right? So, past weather records can be understood as observed outcomes from repetitions. If we observe 100 years weather data, that's data. If we assume that every year Labor Day is the same experiment. Of course, it's just for simplicity. Actual time series analysis will be more complicated than this, but just to tell you how our framework is applied to different types of data, I am telling you this. Okay, so based on these observations, you may think about probability based on past observations. That's time series data. So this is just a simple example, but we can think about similar questions like what is the probability of stock market crashing tomorrow? Stock market crashing like this year, right? Or what is the probability that the GDP growth rate is less than 2% this year or next year? Things like that. Basically, we have similar structure like rain. What is the stock market next year? I don't know. We never observed that like before, but we assume that next year's stock market is basically another realization of the previous ones. So previous ones are, we have already seen a lot of experiments in the past. So based on that, how can we make the best inference about next year, tomorrow, next week, things like that. So that's how we apply our structure to seemingly different setup. Okay. So now let's look at a simple data, right? So now make the example of dice roll. So you roll a dice 200 times, really, and then record the outcomes. So you write down, so number one, experiment number one, number two, up to 200, and you record the outcomes like this, right? 1, 5, 4, 4. So either 1, 2, 3, 4, 5, 6 will be recorded for each experiment, and this is data, right? 200 rows are imply 200 sample size. The problem is, okay, this is raw data, the original data, but does not summarize the data. This is not how you present your data, right? So you have to describe the data well, better than this. That's like this. So instead of listing 200 numbers, you categorize them into different outcomes. Because there are only 6 different outcomes, you may summarize the 200 numbers into 6 frequencies, right? Frequency or count, basically this is the number of occurrences for each outcome. Out of 200, how many times 6 happened? 35. Like 4 happened, 41. 5 happened, 28 times, right? So then, of course, sum of all the frequencies must be the total number of experiments again. That is the sample size. So this is the first step to summarize and describe your data. Super simple, right? But I'm telling you, they are different. You now, when I explain this, you see the difference easily. This does not summarize anything. It is purely original data, and this summarizes it like it is one-time processed. It is a processed information, but when I give you this in an exam as an exam question, I see a lot of students still don't understand if it's raw data or frequency table. So it's a good time to think about that. Think about the differences. And based on the frequency, we can calculate the probability easily. Just divide by the sample size. So out of 200 times, 33 times was 1, outcome 1. So probability is 16.5%. So, and like, so for each outcome, you are going to have different numbers because it's random. You only had 200 experiments. So ideally, you know the true probability is 1/6 for each of the outcome. That is possible only when you have infinite number of repetitions. So in finite sample like this, the probability can be different. Some outcome seems like more likely, others may look like unlikely, less likely than the others. But that's due to randomness. And also, the sum of the probabilities must be 100%. It's obvious, right? So it's a good way to double check if your algebra is right or not. So it is so simple, So I just briefly mentioned this. And as a last question, so I will finish this video with a question. So same data we just saw, and in this data, what is the probability of an even number? I believe it should be easy enough to calculate this probability. So pause the video, like before you start the next video, please try this by yourself. You may use calculator, you may use Excel, right? Just choose your answer and start the next video. I will start with this question in the next video. Okay, it will be continued in the third video. Thank you for watching. See you later.